Good to go. 1 minute. All right, it's 11 o'clock now, so let's please get started. I'd like to welcome everyone to the penultimate press conference of the 232nd meeting of the American Astronomical Society here in Denver, Colorado, on June 6th at 11 a.m. Mountain Daylight Time. This morning's press conference will be on erupting stars and dissolving stars. I am Carrie Hensley, and I am the American Astronomical Society Media Fellow. And today I will be assisted by the American Astronomical Society Press Officer, Rick Fienberg, who's in the back, seated there, who will be monitoring the webcast. And I'm also going to be assisted during the Q&A by Astrobytes author Gaurav Kular, who is seated in the audience. I would like to ask you to please silence any cell phones or other beeping relics of the 1990s that you may have on your person. Don't want to have any interruptions during our presentations today. There have been 3 press releases associated with today's press conference distributed or will be distributed shortly, so please look for those in your email inbox. The webcasts from yesterday's press conferences will be put online shortly. We recorded those successfully yesterday, so those will be up shortly. However, the press kit has already been updated with the presentation slides and press releases from yesterday's presenters. So a brief overview of the ground rules for the press conference today. I will give a brief introduction of our panelists. All panelists will speak in order with no questions in between the panelists, and we'll have Q&A for all 4 panelists after they're finished speaking. So this morning's press conference is on erupting stars and dissolving stars, so everywhere from the star in our solar system, just 8 light minutes away, out to the most ancient stars in our galaxy. Our first speaker on the far left is Jay Pasachoff from Williams College and Carnegie Observatories, who will be talking about motions in the solar corona during last year's total solar eclipse. Next is Thomas Ayres from the University of Colorado at Boulder, who will be talking about searches for possible hazards in nearby stellar systems to our own. Next, we have Sofia Moschou from the Harvard-Smithsonian Center for Astrophysics, who will be talking about a search for candidates for stellar activity in other stars, looking for coronal mass ejections. And finally, we have Andrea Kunder from St. Martin's University, who will be looking at dissolving globular cluster stars. All right, so I'm now going to turn it over to our first speaker, Jay Pasachoff.
Thank you very much, Carrie. I'm very honored and pleased to follow an introduction from a distinguished alumna of Williams College, where I teach. And we have another distinguished alumnus here, Kevin Reardon from the class of '95, who's now at the National Solar Observatory. And they've heard me talk about the sun before, and I now have a few minutes to talk about the sun here. We had a big group going to the eclipse, which we saw under wonderful conditions last year in Salem, Oregon, and we were on the campus of Willamette University. We had 8 of our undergraduates and some professional colleagues from all over the world and some of our alumni, and we saw the eclipse in perfect conditions. I am giving up an eye poster tonight. It is the one that is the extreme corner on the way to the main ballroom, so it's easy to stop by to find it there. And we just had ideal conditions for the eclipse, a lot of equipment set up to study various aspects of the solar corona. And we were able then to make composite images, choosing the best parts out of many different images, because the corona falls off in intensity by a factor of about 1,000 in the earliest solar radius. We were studying, in particular, the coronal streamers that are more or less equatorial, especially at this low point in the solar cycle, but also the polar plumes at the north and south poles, which had been invisible for some eclipses because of streamers at high latitude, but with solar minimum coming, we could see the plumes and see those motions. We do consider our eclipse work the only way that you can get a complete view of the sun on any given day, because the region in the low and middle corona that we see at eclipses is hidden from the occulting disk, by the occulting disk of the C2 coronagraph on SOHO, which you see in red there, and we have pasted on an image here from the Solar Dynamics Observatory at a temperature of about 1.5 million degrees over the center part, which would otherwise be the dark silhouette of the moon. The eclipse is a real thing if you are in space on a satellite such as the new GOES 16 satellite. You can really follow the shadow going across the United States. If you happen to be on the moon, you can look down and see that shadow. If you happen to be in the International Space Station, you can look down and see the shadow. So there's a major darkening that crosses part of the Earth at this time, the United States. We did have a beautiful diamond ring to start things, but then mainly we had the corona for a couple of minutes, and on this image, we've pasted in one of the images from the GOES 16 spacecraft, which has a solar ultraviolet imager facing the sun. It shows gas at about 1.5 million degrees, 195 angstroms in the EUV, but you see a lot of structure in the corona that we are in fact studying. It's very much a three-dimensional thing, like a porcupine, and we're trying to interpret that, and we're working with some people who make magnetic field models to do that. But you clearly see the equatorial streamers and the polar plumes. The conditions could not have been better. There were some prominences on the limb of the sun that helped in our study, and also, fortunately, there were some active regions on the sun, including one near the limb that led to some of the structure that we were studying. The sunspot cycle is quite striking, and you can see very much here as we were in 2018 and 2017 before it. We're very much at a low point. Here is the solar cycle, the most recent solar cycle, where the yellow are days with no sunspots on the sun at all, and you see many of the days have no sunspots at all at the moment, and we were glad to have some for the eclipse. The eclipse is very dramatic, and you stand there, and fortunately these days we have a lot of automation, so we actually can see more of the eclipses than we used to when we had to snap all the cameras ourselves, but here it's very striking. You can see the shadow approach from the right. And it's going to get most of 1 million times darker. Once you're in the middle of 2 minutes of totality, it's actually quite long as somebody else is, or some computer is snapping your images. You can look around and see what's going on, look with binoculars, and get a good view. So it was certainly exciting to be there during totality, and our equipment worked, and we have a variety of things. I have 4 of the 8 undergraduates who were with us last year back at Williams College studying the data right now while I'm here with you talking about some summary things. So we just do have these beautiful composites, but we have a lot of close-ups that we are studying. And you can see the fantastic structure, both radial and also non-radial. We can see eruptions on the sun, which is a reason to fit me into this particular press conference. And again, a pasted-in image over the silhouette of the moon. So we have these fantastic data that show. You can see at left a feature flipping back and forth a little bit. You can see a new plume erupt in the difference of 65 minutes between these two views from our side at Salem and a coordinated view from Carbondale, Illinois. And here with arrows, you can see one of those features that obviously changes over 65 minutes. And this is among the stuff that we are examining in detail. In this image, we have the SUVI image that is showing the more reduced than the one you saw before from Solar Dynamics Observatory in the middle of our further reduced coronal image, and you see it's very sparse in terms of streamers, as opposed to an old image from 1999 where we were at solar maximum, and you can see the extreme difference between solar minimum and solar maximum. So, in conclusion, we have a lot of links at totalsolareclipse.org with our various eclipse expeditions and images that you can see. You can link to this eclipse. And we are looking forward to a series of eclipses, including in total eclipse in Chile in 2019 and in Argentina in 2020, plus partial eclipses in Tasmania in the middle of July and in northern Sweden in the middle of August. And then in the United States, many of you know that in 2024 there'll be a total eclipse coming up from Texas, but some people are not as aware of the annular eclipse rather, that is going diagonally between Oregon and Texas. And for people not in the actual band of totality or annularity, there'll be a perfectly good and big partial eclipse in the United States. So I thank you for listening. I invite you to see more details in the poster or in various things we have posted on the web. Thank you.
It's coming up. It should be coming up. Oh, there it goes. Okay, great. Well, thank you all for coming. I'm going to be talking today about some Chandra observations of some of the nearest stars. And I want to start with my summary, and that is the Alpha Centauri system will be the first stop for interstellar travelers from the Earth. I'll explain that in just a moment. And I'll also tell you that the habitability of planets is affected by things other than just sufficient warmth to allow liquid water to exist on the surface of a planet. There's something called space weather in our solar system, and I call it star weather in other solar systems, that can affect planetary habitability. Now, I will tell you that X-rays are the best measure of this, of the hazard that could be posed by this star weather, and I'll explain a little bit more about that later. And then the conclusion is that an assessment of the 3 stars in the Alpha Centauri system has come up with the conclusion that 2 of them have space weather environments that are very similar to those that we experience around our own sun. And one of them is really, really bad. I'll get to that in a moment. So let me introduce you to the Alpha Centauri system. In the upper left there's a diagram comparing the 3 stars of Alpha Cen with the Sun and Jupiter. So the brightest star is Alpha Cen A. It's a little bit larger and more luminous than the Sun. Its close companion, Alpha Cen B, is a little bit smaller and dimmer than the Sun. And then there's Alpha Cen C, which is a diminutive red dwarf, puny little thing, not much bigger than Jupiter. The age of the system is similar to the Sun, which is good for the development of life. The system is only 4.3 light years away, which is an unimaginably enormous distance, but it's a lot closer than the next nearest stars. And there are 3 stars there, so it's the obvious first stop for interstellar voyagers from Earth. A and B orbit each other in about an 80-year period. The dimensions of the orbit are comparable to those of the solar system. It's an eccentric, egg-shaped orbit. And at closest approach, A and B are about 11 times the Earth-Sun distance apart. And this is sufficient to allow stable orbits for planets in the habitable zones of both stars. And both stars have habitable zones that are similar in size to the Sun. On the other hand, Alpha Cen C, which is also called Proxima Centauri, is at a great distance from the central pair. It's something like 10 or 15,000 times further away from the central pair than the Sun-Earth distance, or what we call an astronomical unit. And on the scale on the screen here, if we were to put alpha Cen C on that same scale, it would be 1,000 feet away, out on the 16th Street Mall, actually next to the hot dog cart up there. And the important thing about alpha Cen C, it actually has a planet detected around it, which is not the case so far for A and B. But alpha Cen C has a tiny, tiny habitable zone, only about 5% of the Sun-Earth distance away from the star. So it's a tiny habitable zone. Now there's a project called Starshot that's been proposed by the Breakthrough Initiatives Foundation to send a swarm of nanobots to Alpha Centauri this century, propelled on by huge lasers on the surface of the Earth, on a 20-year voyage at 2/10 of the speed of light, to fly through the system and snap up close and personal pictures of habitable planets in the Alpha Cen system. Now, as I mentioned before, there are hazards for planets around stars beyond just a simple, there are considerations for habitability beyond the simple warming of a planet. And this has to do with magnetic activity on the star, magnetic storms on the surface of stars like the Sun. And these storms, as we know, we call them sunspots on the Sun, they're caused by the rising of magnetic ropes that are generated deep inside the Sun. They penetrate the surface, darken the plasma, and rise up above the surface in these enormous arcades, magnetic loops. They're filled with very hot plasma, millions of degrees. They radiate ultraviolet and X-rays, and occasionally flare. The fields stretch out and wrap up against each other and snap like a rubber band, emitting a huge flare. And then associated with these flares are mass ejections, or plasma blobs that fly out through the solar system. And you'll see one of those in the movie in a moment. As the fields wrap up and get stressed and snap like a rubber band, there's a huge flare, and then this plasma lifts off from the surface of the Sun and flies out through the planetary system, affecting all the planets. Now, associated with this magnetic activity, with these sunspots on the Sun, star spots on other stars, you have persistent ultraviolet and X-ray radiation. And there's a hot wind that comes from these active regions that kind of sweeps out through the corona and shapes the structures that Jay was showing in his beautiful eclipse pictures. And then there are occasional flares, as you saw in the movie, and these mass ejections that increase the radiation hazard by orders of magnitude. Now, this space weather, or star weather, if it's on another star, has two consequences for life. First, the high energy radiations, the ultraviolet and X-ray, can just simply sterilize planetary surfaces, unprotected planetary surfaces, and that's bad for life. There's a more insidious effect, and that is that the hot wind, the ionizing radiation, and these mass ejections from flares can strip off atmospheres of planets. And this is a fate that's thought to have befallen Mars in our own solar system. In the early days, when the Sun was back in the formation of the solar system, when the Sun was much more active than it is today in a magnetic sense. So the best tracer of this activity are X-rays. And we can measure X-rays in nearby stars using the Chandra X-ray Observatory. So now I'm going to tell you about a project that I and my colleagues have been carrying out for now more than a decade with the Chandra X-ray Observatory to measure the X-ray emission of the two main components of Alpha Centauri, that's A and B. And I've tried to capture these observations in the form of a little cartoon movie. And so what you'll see in this movie are two dots, a little yellow dot for Alpha Cen A, an orange dot for Alpha Cen B. The size of the dots is proportional to the X-ray brightness of the two stars. And you'll see in this initial view that Alpha Centauri is bigger or brighter than its larger companion, Alpha Centauri. So the smaller star is brighter in X-rays than the larger star. This actually is typical of cool stars in general. These observations cover 13 years. The most recent observation was made about 2 weeks ago. The observations are about 6 months apart, and each pointing on Alpha Centauri is about 3 hours long. So you'll see these two dots kind of dance across the screen, and the general motion from lower left to upper right is called the proper motion of the system. This is the transverse space motion of the Alpha Centauri stars across our sky. But you'll also see the two dots drawing together and then spinning around each other partially. That's the orbital motion of the Alpha Centauri stars. And on top of that, there are some additional wobbles that you'll see, which are due to parallax. And that is the effect that when the Earth goes around the sun and Chandra is attached to the Earth, a nearby star, and you can do this experiment, this is Astronomy 101, you look at your finger and this way and that way, and so nearby stars appear to move against the background. Here's the movie. Oh, and then of course there's a bonus. They're observations. Those grayscale images are actual observations by Chandra, and then the dots fill in all the other. So you see the orange dot is now getting bigger, and you see the little wobbles due to the parallax. The orange dot's getting bigger, and that's because Alpha Centauri's star spot cycle is beginning to peak. Now it's getting smaller because it's beginning to fade away, and A is starting to get bigger. And then pretty soon we're going to get to the final observation. There it is, and then they go off into the sunset. Okay, so here's a chart that shows basically the radiation hazard in the habitable zones of both Alpha Centauri, Alpha Centauri, and the Sun. So on the vertical axis is the X-ray dosage in the habitable zone. On the lower axis is year, and this program started in late 2005 and continued up until 2 weeks ago, as I said. And at the top of the diagram, the orange dots are for Alpha Centauri. In the middle of the diagram, the darker dots are for the Sun, the X-ray light curve of the Sun over the past several years. And then the yellow dots in the bottom are for Alpha Centauri. Now, if you look at the Sun, and Jay showed a sunspot cycle diagram earlier, you see that there was a minimum in 2019, and the X-rays started to rise again as there were more and more sunspots on the surface of the Sun. And finally, around 2015, the X-ray cycle peaked out, and now we're in a declining phase. The period's about 11 years for the Sun. Now, in Alpha Centauri, in the upper part of the diagram, you see in the orange dots, it was beginning to decline already in the first observation, late 2005, and bottomed out a few years later, then began to rise and declined again and rising again. So we've seen a complete cycle now of Alpha Centauri with the same instrument, with the Chandra high-resolution camera, which, by the way, is the only instrument only X-ray instrument, cosmic X-ray instrument, that's capable of resolving the two stars in the current epoch, because they're actually quite close together now. And so we've seen a complete cycle of Alpha Centauri. Now, Alpha Centauri is a little bit different. It was kind of flatlining for about 5 years, between 2005 and 2010. It was kind of in a star spot lull, if you will, in a low state in terms of its X-rays. Then it started to climb up very slowly in 2010. And by about 2015 or 16, it had reached what we believe is a maximum. And we now think that it's beginning to decline towards a minimum, although, of course, time will tell. Now, the interesting thing here is the Alpha Centauri has a much longer cycle than the Sun. It's probably 20 years compared to 11. It's also lower in X-rays, while Alpha Centauri has a shorter cycle than the Sun, and it's higher in X-rays. Now, these stars, as I mentioned before, are very similar to the Sun in size, mass, and in luminosity. Yet their cycle behavior, which is caused by a magnetic engine inside the star, is somewhat different. Now, notice that Alpha Centauri is not on this diagram. And that is because it would be way off scale. Its normal X-ray brightness in the habitable zone, which remember is very close to the M dwarf, is 500 times higher than the sun. That's a lot. And during big flares, it rises to 50,000 times the X-ray dosage that we would receive from our sun. So for future voyagers to the Alpha Centauri system, what sort of conditions might they expect to encounter in terms of the star weather? And so let's just go along here. Well, for the sun, well, we think the sun is somewhat habitable. I mean, after all, we have a highly evolved technical civilization on one planet, at least, around the sun. And it is, in fact, habitable from this star weather perspective, except for those occasional super flares that might happen, which would burn out all our cell phones and destroy GPS, which would not be very much fun, but that's another story. So what about Alpha Centauri? Alpha Centauri gets a big smiley face and a thumbs up, and that's because its X-ray hazard is much lower than the sun, so that's good. Alpha Centauri, well, we have a kind of a quizzical face there. Its hazard is higher than the sun, because this normal X-ray flux is 5 or 6 times higher than the sun, but it's not crazy higher than the sun. It is probably okay. And what about Alpha Centauri? See, I think you're seeing where I'm going with this. Yeah, so just don't go there. There is a planet that's been detected around Alpha Centauri, and it would be absolutely a miserable place to be, let me tell you. So here's a summary again. The first place that we humans are going to go in our interstellar travels will be Alpha Centauri. It's just a no-brainer. The habitability of planets in general, and certainly around the Alpha Centauri stars, is affected by magnetic activity on the stars, the star weather effects. And as I've told you, 2 of these Alpha Centauri stars, the 2 most sun-like Alpha Centauri stars, have sun-like radiation environments. These would be the best places for life as we know it to exist, except we don't know whether they're planets yet around those 2 stars. It's a very difficult task to measure these planets. And as I've also told you, the 3rd star, Alpha Centauri C, or Proxima, is just a terrible, terrible place. You wouldn't want to go there unless you wear a big lead suit. Okay, well, thanks very much.
All right. Good morning, everyone. My name is Sofia Moschou, and I am a postdoc at the Harvard-Smithsonian Center for Astrophysics. This is a work in collaboration with my colleagues at the Harvard-Smithsonian Center for Astrophysics and UMass Lowell. We cannot really image directly CMEs in other stars, so we need to look at indirect methods of observing them. And this is what I'm going to talk about today. Possible stellar CME coronal mass ejections. We started last year by analyzing one of the most extreme events we have ever seen and could be associated possibly with the coronal mass ejection. It was observed in 1999, an extreme super flare, which was 100,000 times more energetic than any solar flare that we have ever seen, and it was observed at the Demon Star, as the Algol binary system is else known. So we estimated the coronal mass ejection characteristics for this associated with this particular event, and we got a monster CME obscuring this Demon Star flare, and we estimated a mass of 100,000 times more than the most massive solar CME, and a kinetic energy of about 1,000 times of the most energetic solar CME. But what do we know from the sun? There are several statistical studies that have associated the energy of the X-ray flare, which you can see in the horizontal axis, with the associated CMEs, which you can mass, which you can see on the top panel, and kinetic energy on the bottom panel. These studies have concluded that more energetic flares are associated with more massive and faster coronal mass ejections in the Sun. And the question really comes down to, does this trend continue to more active stars? So when we go and observe super flares, are the CMEs equally even more massive and even more energetic and fast? This is important, as Thomas described before, in case we would like to characterize exoplanetary environments, and we need to do this beyond just the original temperature-based habitable zone definition. We need to take into account extrasolar space weather, which is CMEs and flares. So when we turn our radio telescopes in other stars, in more active stars, such as, for example, M dwarfs, which are 70% of the stars in our galaxy, we see them flaring all the time. We see flare after flare and after flare. But what happens with CMEs? As I said, we cannot image them directly, but there are observational indications where they could be present. The first observational method is through Doppler shifts. So essentially, we are measuring the speeds of material moving towards us. As I'm showing here an example of mass moving upwards with a speed of about 600 kilometers per second, higher than the escape speed locally. And the second method is through X-ray absorption. So while we are observing an X-ray flare, at the same time we have a peak in the column density, as I'm showing on the first graph. And here we explore the scenario that this peak is due to a coronal mass ejection that is obscuring the X-ray source. So it's between the observer and the X-ray source. And then for the algol event, we saw that there was a gradual decay that is consistent with the CME expansion with a constant speed. And this is all part of a paper we published last year. So when we put the algol event in the same graph with the solar events, we see that taking into account the spread in the solar events and the errors for the algol event, that they lie in the same trend. Now we expect that the other candidates, the other coronal mass ejection candidates, will populate the space in between the solar, bracketed between the solar and the algol event, as we can see here from some preliminary results that we've been working on lately. So they indeed lie, they fill in the gap in between the solar events on the lower left and the algol flare and associated CME on the top right part of the graph. And we see that there is quite a big spread. So finally, I would like to conclude by saying that we really need to start taking into account extrasolar space weather and have considerations beyond the purely temperature-based initial habitable zone definition. In particular, we need to account for coronal mass ejections and flares that, as Thomas explained earlier, they can have devastating effects to planets orbiting these active stars. Now, the solar trends, the solar events are showing a very clear trend. When we have a larger flare, it's most probably associated with a large CME. So we expect when we see these super flares, when we see them all the time in other stars, we expect to have monster CMEs associated with them. But we don't really see them for the moment. We have only about a dozen possible CME events, and we are gathering them up in a paper that we are writing at the moment. And the question for this observational discrepancy really comes down to whether this is a purely observational bias or whether there is actually a fundamental mechanism that could suppress the CMEs in these more active stars, and they are not even ejected at the first place for us to observe. In order to tackle this problem, we need definitely more observations, and we also need theoretical work to examine these different regimes where active stars live. For example, we need to examine the effects of very strong magnetic fields that are often observed to be associated with M dwarfs. I would like to finish by thanking the NASA Living with a Star grant that has been supporting this research, and thank you very much for your attention.
Hello, I would like to talk about work that was carried out at St. Martin's University, where we have discovered dissolving globular cluster stars around the globular cluster NGC 6441. This result was published in March by the Astronomical Journal, and the reference is listed below on the slide. Since then, however, the Gaia space satellite has released positions and proper motions of more than 1 billion stars all over the Milky Way galaxy. We have checked our dissolving globular cluster stars with the observations released by the Gaia Space Catalog, and we found that, indeed, Gaia also shows that their proper motions are exactly consistent with these dissolving stars belonging to the cluster. So our results stand on very solid footing. Globular clusters are some of the oldest objects that exist in the universe. So just like archaeologists use fossils to reconstruct the history of the Earth, so scientists use globular clusters to reconstruct the history of the Milky Way galaxy. It is curious, however, that the globular clusters within the Milky Way bulge, which is the central part of the Milky Way, the red circle shown in the diagram of the Milky Way galaxy, has globular clusters that have bizarre properties that are not seen in globular clusters elsewhere in the Milky Way galaxy. And it is not yet known or understood why the properties of these globular clusters are so different in the bulge of the Milky Way galaxy than other places. Our results indicate that one reason that these bulge globular clusters are different is because they have dissolving stars, meaning that they were much more massive in the past. And as they are being accreted by the Milky Way galaxy and moving through the Milky Way galaxy, they are now losing stars. So we are showing that the globular clusters in the bulge were more massive in the past, such as if they used to be dwarf spheroidal galaxies. The globular cluster that we looked at in particular is located in the galactic bulge. It's called NGC 6441, a very exciting name. It is the fifth most massive globular cluster in the Milky Way. So if we have the analogy of globular clusters being dinosaur fossils, this wouldn't be the Tyrannosaurus rex of globular clusters, but it would still be a ferocious, meat-eating dinosaur such as a velociraptor. The problem with studying globular clusters in the bulge of the Milky Way, such as NGC 6441, is that there are a lot of stars in the center of the Milky Way galaxy. And so it is very difficult to disentangle which stars actually belong to the cluster you're looking at and which stars are in the way, are in the field, either foreground or background objects. Another difficulty is that there's a lot of gas and dust in the bulge region of the Milky Way galaxy, and this affects the light coming from stars, so it's hard to get a good picture of the stars in the central region. Our approach was to look at RR Lyrae stars, not only in the globular cluster, but also around the globular cluster. RR Lyrae stars are a special kind of star. They are called distance indicators. So if you can find these stars, and if you know their brightnesses, you can immediately tell what their distance is. And so this, as a first approximation, you can say, are the distances of the RR Lyrae stars in and around this globular cluster consistent with the star being in the cluster, or do they have distances that suggest they're either in the foreground or the background of the globular cluster? However, these stars are relatively faint, so they are more difficult to observe, and there had been no radial velocity measurements of the RR Lyrae stars around this globular cluster and inside this globular cluster. And so this is what we at St. Martin's University did, was find radial velocities, how the stars were moving through space. And these are our results. On the right-hand panel, the galactic latitude and galactic longitude of the globular cluster is shown, and the dotted line shows the extent of the globular cluster. All of the red symbols show the Aurora Lyrae stars that are associated with the cluster. And you can see the Aurora Lyrae stars that are outside the globular cluster. There's quite a few of them that we observed outside of the globular cluster. Those that are blue triangles have radial velocities, what you would expect if they did belong to the cluster. The right plot that shows the radial velocity as a function of distance from the center of the cluster shows that all the Aurora Lyrae stars within the cluster have the same radial velocity, but also even if you extend further outward of the globular cluster, there are still Aurora Lyrae stars with radial velocities consistent with that of what you expect if they were part of the cluster. However, they are quite a ways outside of the extent of the globular cluster, such as if these stars were being dissolved from the globular cluster. The globular cluster moves through space on this dotted line that is shown in the galactic latitude and galactic longitude plot. That is how the globular cluster is moving through space over time. And you can see that most of our candidates for being dissolved also lie across along the line of how the cluster is moving through space. And this is exactly what is predicted for debris for dissolving cluster stars. Now this plot right here shows now the Gaia proper motions, the Gaia results, exquisite observations that have never been able to be done before of the Aurora Lyrae stars within the cluster and also those that have radial velocity measurements that we have obtained. And you can see that the Aurora Lyrae stars within the cluster have proper motions that are all consistent with each other, that clump together. But more than half of our dissolving cluster stars have the exact same proper motions, further confirming that these stars used to be cluster members that are now being tidally disrupted. And the right panel again shows our globular cluster NGC 6441 and the tidal extent, and the red symbols show these stars that are bona fide cluster members that are now being disassociated from the cluster. So to conclude, we have found that the globular cluster in the bulge, NGC 6441, definitely has extratidal Aurora Lyrae stars, and these extend out to 1/4 degree from the cluster. And this indicates that NGC 6441 must have been more massive in the past. It must have been a much larger globular cluster, or perhaps even the nucleus of a dwarf spheroidal galaxy that is now accreted by our Milky Way and is slowly losing stars. And this is the first time that such stars were detected, such dissolving stars were detected around NGC 6441. Thank you.
All right, we have our panelists back up here now. So we can now begin our question and answer. So a reminder for the on-site journalists and audience members to please wait for the microphone, which Megan, in the back is going to bring around to you. Please speak into the microphone so our observers on the webcast can hear your questions. And also please state your name and affiliation before beginning your question. For the journalists tuning in from the webcast, please type your questions to Rick, who will relay them to our presenters.
Hi, Dick Henry, Johns Hopkins University. A question for Tom Ayres. Tom, we've found thousands and thousands of planets around stars, and yet Alpha Centauri A and B, does it mean there are no planets there? Why haven't we found them?
Yeah, that's a very good question, Dick. One of the reasons, it's very difficult, first of all, to find planets around other stars. And as you know yourself, most of the planets that have been found so far, say by the Kepler mission, have been transiting planets. So there has to be a special orientation of the system in order for a transit to occur. And that's a very small percentage of stars. Now the Alpha Centauri system is tipped in our line of sight We see it almost edge on, but not quite enough that, yeah, I know, just not quite enough, that if the planetary orbits were co-aligned with the stellar orbit, that we would see transits. Now, transits have been looked for very hard. There was a proposed planet around Alpha Centauri B a number of years ago using a radial velocity technique by a European group. And they did quite a careful job, but their result was criticized almost immediately because at the time, Alpha Cen B was rising in its activity cycle. And as you know, when a star is more active, it has more star spots on its surface and more small flares and events that can distort the spectral signatures of the radial velocity of an orbiting planet. So apparently what happened, and that result was withdrawn, that discovery of a planet around Alpha Cen B was withdrawn several years later, and apparently was this activity-induced signature, radial velocity signature that was at fault. Now, that, however, did not prevent the discoverers from obtaining a lot of space telescope time to search for transits of this putative planet around Alpha Cen B, but they didn't see anything. The main problem in the contemporary era is that the two stars, you have two very bright stars that are very close together. They're only 4 or 5 arc seconds apart. And that's going to be the case for a number of years to come. And so it's the interference, the brightness interference of one star on the other that makes radial velocity searches, photometric searches, and other types of searches much more difficult now. But there are a lot of people trying to do this. It'll probably require some sort of occulting system, chronograph system, to do it right.
John Wenz, freelance, and this is also for Dr. Ayres. I guess when what does it mean in more practical terms that 5 to 6 times more radiation is coming out of Alpha Centauri B? Is that something that, if there were a pretty decent Earth analog there, that it would be battered too much by that radiation to hold on to the atmosphere, or what are the kind of ways that a planet might fare under that slight uptick in radiation?
Yeah, that's a very good question. So we know in our own solar system, the planet Mars was thought at the beginning to have a pretty substantial atmosphere, enough to maintain, and a greenhouse effect, enough to maintain liquid water on the surface. There's evidence for shallow oceans in the northern hemisphere of Mars. Now, the interesting thing about the solar system that may not apply to other planetary systems, maybe sort of a happy accident for us, was that there was a phenomenon called the late heavy bombardment around 600 or 700 million years after the formation of the solar system. And this essentially erased and rewrote all of the planetary surfaces and atmospheres. And so this is fairly late in the development of the solar system. Now, stars, when they're young, are much, much more active than older middle-aged stars like our sun. But the solar system apparently escaped that period of extreme activity simply by the fact that the planets were kind of reconstituted at this relatively late stage. Nevertheless, the sun was still pretty active at that time, and we know a lot about that period because there's something called the Hyades cluster. It's a nearby galactic cluster that has a lot of solar-type stars that are of that age. And they have X-ray luminosities that are sort of 10 or 15 times higher than the contemporary sun. So that's more than Alpha Cen B, but not all that much more. So it might be, that's why I put the kind of quizzical face for Alpha Cen B, because the space weather conditions there might be sufficient to remove the atmosphere of a small planet like Mars that does not have a protective magnetic field and does not have a strong enough surface gravity to hold on to that atmosphere. So we think that it only took, 10 or 15 times the kind of space weather activity of our contemporary sun to basically blast away the atmosphere of Mars and make a planet that, is technically in the habitable zone, not very hospitable at all.
Over to the right here.
Thank you. Vanshri Bhalotia, freelance. I have a question for Dr. Andrea Kunder. I really enjoyed your talk, by the way. So I just wanted to ask, so you said that some of the stars were dissolving from the cluster. So I was wondering, what was the reason for some of these stars to dissolve, or like to escape the cluster? Because the cluster has so much gravity. So why would these stars be? Is it the central black hole of the Milky Way, or? I don't know, just wondering. Thank you.
Yes, thank you. So the central part of the Milky Way galaxy, the bulge, does have a lot of mass in it because there is a black hole in the center. And some stars won't be as gravitationally bound to the cluster as other stars. So the very central part of the cluster is where the gravitational attraction is the strongest. And so those stars are most likely to stick together. But if you're further outside from that core, then it is the gravitational interaction with the cluster will not be as strong. And so it's more likely that then the mass of the bulge will pull that star out, and it won't be following the cluster anymore, but will be stripped out from that way. So it's just a function of how gravity works. The closer you are to something, the stronger the gravity is. If you're further out, then maybe something else will, another mass source will have gravity that affects that star more.
Eric Mack for CNET. Another question for Professor Ayres. Is there any possible alignment in which those really strong flares from Proxima Centauri could affect the habitable zones of the other two stars?
Yeah, that's an interesting question. Alpha Centauri is so far from the main pair that it's very unlikely. Actually, Alpha Centauri, although I portrayed it as kind of like the Algol demon star, it's not really terribly active compared to some other M dwarfs like EV-LAC that we saw, which is just popping off these super flares all the time. The distinction is that the habitable zone around Alpha Centauri is so close to the star that any activity is just magnified. So the flares really are not all that big compared to some other M dwarf stars. It's an old M dwarf star, it's 6 billion years old. So, and it really is quite far. It's almost a tenth of a light year away from the other stars. In fact, in our nighttime sky, Proxima, which is technically the nearest star, it just happens to be on the sunward side of the system, is, I think it's a 9th or 10th magnitude visual star. So you couldn't see it without binoculars. And that's the closest star. Now, if you were on the Alpha Centauri system, Proxima would still be a pretty dim star. It would only be 4th magnitude. It would be a naked eye star. And it would only be distinguished by the fact that it would be moving pretty fast across the sky and would show this huge parallax swing, much like the giant planets in our solar system do. But it still would be a faint star. So it's not going to really affect the main pair.
Any questions in the room or on the webcast? Rick?
Yes, we have one here from Javier Barbuzano, who's a freelancer who's reporting for Sky and Telescope this week. His question is for Andrea Kunder. You said that this is the first time that these dissolving stars have been detected around this particular globular cluster, NGC 6441. Have they been seen around any other clusters, more massive or less massive?
Yes, that is a good question. There is another globular cluster in the bulge called Terzan 5. This is a globular cluster that also has very bizarre properties. And there has been indications that this cluster also has dissolving stars around it as well. It is, again, it's very difficult to do this kind of work within the bulge, given the crowding and not being able to disentangle which populations belong to where. But now that Gaia has released also space motions, this is starting to be done. But Terzan 5 is the other globular cluster where this has been seen as well. And I think there's two Nature papers talking about it also being one of these more massive systems that are now look like globular clusters in the bulge.
Okay, there are no further questions on the web.
I actually have a follow-up question for Andrea. What is the time scale for complete dissolution of a globular cluster, and is it short enough that we expect there to have been more globular clusters in the past?
Oh, gosh. So the time scale depends on the initial mass of the system as well as how gravitationally bound it is. So this whole field of globular clusters being remnants of dwarf spheroidal galaxies is still relatively new because we have seen these peculiarities in globular clusters. And yes, so so timescales, yeah, so it would vary greatly as to the progenitor mass and the progenitor density. But I suppose there could have been globular clusters that started out as globular clusters that now have been dissolved. And as we gather more information from Gaia or get more chemistry of stars, maybe we'll be able to place some of these systems together.
Great, thanks. I think we have a question up here with Nola.
Hi, Nola Red, freelance. Okay, I'm just going to ask like the really stupid, obvious question that I'm pretty sure I know the answer to, but when you say dissolving stars, you mean as in the cluster's dissolving, the stars are just leaving. You don't mean like dissolving, like I'm melting, right?
Right. So they're dissolving into the Milky Way galaxy, but they're still there. They're still burning.
Okay, that's what I thought, but I just wanted to be sure. And then my other question was for Dr. Moschou. So you said it's possible that these extremely active stars could be kind of swallowing up CMEs so that we don't see them. What sort of processes might explain that?
Yeah, so that's a really good question, and it's a part of active research. So we see this in the sun as well. When we have an active region with a strong overlaying magnetic field just on top of this active region, we see that this can be a suppressing mechanism, essentially keeping the flare in. So when we have reconnection below this strong magnetic field, the CME, the material, will want to be ejected, but it's not strong enough to make it through out of this strong magnetic field. We are working on this currently, actually, and my colleague Julian Alvarado Gomez is doing several simulations on this, where we took a magnetogram of the sun, where we saw a strong CME and flare event, and then we put a dipole, a strong dipole, large-scale magnetic field of 100 Gauss. The magnetic field of the sun is normally of the order of 1 to 10 Gauss or so, the global one. And then this suppressed all the CMEs, the entire range of the CMEs that we see for the sun. And then we kept increasing the strength of the CME, the poloidal flux that is. And finally, at some point, CMEs were able to break through. But they need to have enough kinetic energy. So there needs to be a humongous flux, a very strong force that makes the CME to go through and break through this very strong overlaying magnetic field. So that's the mechanism.
Steve, up here in front.
For a stupider question, and this is for the first three, any of the first three panels. In Tom's and Sofia's presentations, the theme was there that you have sufficiently great space weather that things are going to be inhabitable. Are we sure there is not some minimum level of space weather or solar stellar weather that may be beneficial?
I was going to say the opposite of beneficial, then I'll turn it over to you. But we solar astronomers, as Dr. Marin knows, talk about the Carrington event in 1859, which was bigger than any flare we've had recently. And an event like that could devastate all our electronics and our satellites. And of course, that wasn't necessarily the biggest possible in our solar system. So I'm more worried about major disruptions than I am about beneficial projects.
Yeah.
Go ahead.
Okay. Yeah, I think you might be right, because life as we know it requires evolution, and evolution is strongly mediated by radiation, particle radiation particularly, and that comes from the sun, and it could a low level of radioactivity or radiation from the sun could enable life or could help life along. But I mean, on the other hand, in the terrestrial setting, there's radioactivity in rocks that's just naturally there. There's also cosmic radiation from sources, external sources, that could provide the same kind of low-level background radiation. But again, stars were much more active in their youth and decline as they get older. So they could have kick-started life early on, but then when life becomes more complicated and technological, as Jay was saying, and Sofia, it could become a hazard if it's too much.
So I would like to echo what both of the previous panelists said, and I would like to add that the mechanism that I described previously of the suppression mechanism for the CMEs, so when you have a large-scale magnetic field topology on top of your active regions, smaller scales, we see that this mechanism actually is very consistent with the low energy scales at the sun as well. So the magnetic field, the large-scale magnetic field of the sun, which is of the order of a few Gauss, 10 Gauss or so, makes a threshold which is about 10 to the 26 or so, and really explains very well the lower limit of the minimal activity that we see in the sun, and so that makes us even more sure that this is what's going to happen in other stars as well.
As most people here know, we are in the era of multi-messenger astronomy. So we've been talking about only a minor part, the photons, and now we've been hearing about the particles. So I take this occasion just to mention the gravitational waves. I haven't quite figured out a mechanism that they would have affected us at some close supernova or some closer things. But let the record show that we've only been talking about 2/3 of the kinds of detections in space that we are now making.
My question's for Jay Pasachoff. Jay, I'm wondering if you know what is the largest number of solar eclipses that has been attended by a single individual, and who currently holds that record?
Would you repeat, Dick? What, did you say total solar eclipses or solar eclipses? Well, there actually was an article in the New Yorker in Talk of the Town in August, which was questioning why the 3 people who have seen the most total solar eclipses, which is 34, were all from the Bronx. And I can supply that reference on request, or it comes up in Google.
Hi, my name is Ekta Patel. I'm from the University of Arizona. My question is for Andrea. So I know that there are several globular clusters that are associated with stellar streams. So I was wondering if the dissolution process that you described has a connection to the formation of stellar streams, or if it's thought to be totally a different process, or what your thoughts are on that.
Yes, so there are some globular clusters that have streams that are probably not cores of dwarf spheroidal galaxies, such as Palomar 5. So it is unclear for NGC 6441 what is the reason for the dissolution of the stars. So right now we've detected stellar dissolving stars around this cluster, and now the next thing would be to apply for more time to follow this up and see, does it look like one of these narrow bands of streams that we see, or is it more of a diffuse kind of halo that we see around other globular clusters such as NGC 1851? And so, yeah, that would be the next thing, is try to go out to a larger extent and quantify that more. But I think the first thing is showing that there is something there, so that we can get the resources and the time to dig deeper into what that means.
Yeah, one more question up here in the front.
Hi, Mackenzie Joy, University of Georgia. I had a question for Andrea. Is there a way to determine a possible dark matter component of the cluster? And would that be necessary to figure out if it was once a dwarf galaxy?
Yes, so that is not something that I know that much about, a dark matter component. That would be very exciting to look into that. If you were to look at a dark matter component, you would want to do it for the most massive globular clusters, and this one is definitely one of the most massive globular clusters. So that would be something that is good. Recently, there was a black hole discovered in a globular cluster, NGC 3201, and so that would also be something to look for. And because if you do see a black hole in the center of a globular cluster, that would also indicate that it was once a larger member. So now we're it's something that we should look for in this cluster now that we realize that there's some dissolving stars, as well as trying to see if we can find any kind of dark matter component as well. Those would be the next very exciting steps to do.
All right, that's all the questions we have time for today, so that concludes our morning press conference. So please let's thank our 4 panelists. And also a big thank you to everyone in the audience for attending and everyone who tuned in on the webcast. Our next press conference, which is the final conference for this conference, will be today, June 6th at 3 p.m. Mountain Daylight Time. Those of you who have signed up to attend the press dinner, that's taking place this evening at 7:30 p.m. at La Loma. It's just a few minutes walk from the hotel, and there is a map in the press office if you need directions. Thank you.
Thank you.